So we're going to the next question, and this one was sent to us by Neto Mawela. A big shout out to you, Neto. And also a special shout out goes out to the breadwinners for allowing the kids to watch TV. Thank you, parents. Please let them watch 2 to 5 o'clock every weekday from Monday to Thursday. We are doing Term 2's work. So I hope you guys at home will also ask your parents to allow you to watch TV only between 2 and 5. Right. So Neto's question is a nice question. It's one that is based on inverses, right? It's specifically about inverse graphs. So I want you guys to see, if you haven't seen inverses in your life before, I hope this is going to open your eyes. If you have seen them before, I hope you're going to help you to understand even more about what is going on when it comes to the whole concept of inverses and inverse graphs and those kinds of things. So let's begin this question first of all by something very important. The notation, right? Before we even read the question, and I'm going to be quick now, guys, so that we can have more time to even go back to those analysis questions that involve a lot of graphs sketched on the same set of axes that look very confusing. I want to do more questions that look like those because I saw one of them that you guys wanted us to look at. So I hope that will help you. But before we get there, let's finish off the last part of the theoretical questions that you wanted us to look at. So the notation is very important. If someone writes to you f of x, what this implies is function, right, of x. This is a function of x. It's very important for you not to confuse your facts, right? Names of functions. This current function is called f. Its name is f. Now, it could have been anything. It could have been g of x. That will still mean it's a function of x named g. It could have been h of x. That's another function of x named h. So the one I wrote in white is the function of x named f. Right. Now this here, beautiful people, with a prime, that there with a prime, is not a function, but is what we call the derivative of the function of x. So derivative of f of x, which means it is the derivative of a function of x named f. Right? If you just replace all those words that I wrote here, all these words that I wrote here, if you substitute them here, mathematicians, substitution, big business, all those words, this means the derivative of a function of x named f. Now, a derivative is something that we're going to probably look at next week because it is what we call the gradient at a point. You guys are familiar with what we call average gradient, y2 minus y1 over x2 minus x1. This one here is what we call instantaneous gradient, gradient at a point, right? And it is a concept of differential calculus, and we haven't yet started looking at that. We're probably going to start looking at that maybe on Thursday or maybe next week. So keep working on what we're working on now, and maybe if you have questions on this, you can then save them for next week. Right. Now this here with a minus 1, right? F to the power of minus 1 implies the inverse, right? The inverse of f of x, which means it is the inverse of the function of x named f. Please don't confuse those things. Those things are different. And maybe I might also want to add that this that you're looking at here is different from f of x, right, to the power of minus 1. That is totally different because that one means 1 over f of x. That's f of x to the power of minus 1. So the minus 1 you see here for the inverse part is not an exponent. It's a notation of denoting inverses. So please do not confuse those things. We get a lot of confusions when it comes to this. Even when you are reading exam questions, be careful about what the examiner is asking you. Are they asking you about the inverse or are they asking you about the derivative? Right. So what is an inverse? What is an inverse? Well, an inverse is an anti-function. It's the opposite of a function. Right. So we have already explained that from your transformation, which comes from grade 9, an inverse is the reflection, right? It is the reflection of any object, right, by the line y is equal to x. This is a very important thing that you need to understand. Even when we ask you to sketch a graph and its inverse on the same set of axes, you will need to show us that line of reflection. It means that each object is the mirror image of its inverse, where the mirror line is the line y equals to x. Right. Now, when you're reflecting stuff by the line y equals to x, like we've already said, what happens is all your x's become y's, right? And all your y's become x's. That's it. There's nothing else. That's all there is to it. If it was in my class, I would say class dismissed, but we are here, so we want to see how does this really apply in the context of solving problems. But essentially, if you think about it, the reflection of an object by the line y equals to x will produce the inverse of that object in terms of functions. And all your x's will just become your y's, and all your y's will become your x's, which means your y-intercept will become your x-intercept, and your x-intercepts will become your y-intercept. Your domain becomes the range, and the range becomes the domain. They literally swap. Everything literally swaps. So how do you find the equation of the inverse graphically, or maybe algebraically? How to find, this is what is important, how to find the equation, right? If you are asked to find the equation of the inverse, you do two things, only two things, guys, right? Number one, what you will do is exactly what I said. You swap x and y, and then number two, you then make y the subject of the formula, and that will be it. I'm essentially saying the same thing twice here. I said all your x's becomes y's, and all your y's become your x's, because that's what you normally get when you reflect any object by the line y equals x, right? So in order to find the equation of the inverse, you will always swap your x's and y's. Wherever you see x, you put y, and wherever you see y, you put x, and then after that, you try to make y the subject of the formula, right? So let's go to the first question that is going to start showing the application of this concept in real life, application of this concept in a problem, right? So this is Neto's question, Mawela's question. Let's look at this question. It says to us here, we are given f of x. It says to us here, if f of x is equal to 3x plus 2, right? Where, okay, x is less or, okay, there's no restriction. That's for the second one. There's no restriction for this one. We just told that f of x is 3x plus 2. Number one, there's the question. Number one, we have to find f2, the minus 1 of x, right? And then number two, we have to sketch both f of x and also its inverse graph. So that's essentially what Mawela wanted us to do, the first part of what Mawela wanted us to do. Now let's go and see how can this be executed in terms of solving this problem. So here are the solutions, right? Mawela, no complications here. Number one, I was told that f of x is equal to 3x plus 2. So I'm going to change my f of x and call it y, the general form. Y is 3x plus 2. And then I'm then going to start following my process of finding the inverse, because you're asking me to find the inverse there. Find f to the power minus 1 of x. That's asking us to find the inverse. And how do we find the inverse? You start by swapping your x and y. So for me to find the inverse, I'm going to swap the x and y. So wherever I see y, I'm going to write x, but my 3 stays the same. And where there's x, I'm putting y, and I keep back my 2. That's actually what you do. Where there's y, you put x, and where there's x, you put y. Nothing complicated there. You can clearly see what I did. I changed my y to x, and I changed my x to a y. Right, now once you're done doing that, you then make y the subject of the formula. I'll subtract 2 on both sides. I'm going to get x minus 2 is equal to 3y. And then you just divide both sides by 3. Your equation ends up being x minus 2 divided by 3. Therefore, our inverse graph of x is going to simply be x minus 2 divided by 3. I was not told how to express it. I'm just going to write it as this form, because sometimes they tell you that they want you to write it in a form y equals to something. Very important. So that will be the answer for the first part. Right. Now the second part says we need to sketch the graph of f of x and its inverse on the same set of x's. So f of x is 3x plus 2. Let's try and draw the first graph and see what we're going to do. So I'm going to say to the examiner, okay, if we know, right, if we know that f of x is 3x plus 2, and we have to draw this we can all see that this is a straight line. This is a linear function, right? Now, what do you know about a linear function? Well, to sketch a linear function, there's quite a lot of things that we know. For example, I know for a fact that because of this plus 3, right? This is now to add information just to help you with analysis problems. This 3 is positive, right? That means we're expecting to get an increasing straight line, right? This is not necessary, but I'm doing it just for your education so that you guys benefit more from this question. It's going to be an increasing straight line. And this plus 2 tells me that its y-intercept, the y-intercept of this line is going to be 0 and 2, right? So I can actually start drawing the graph. I know for a fact that those are going to happen. But if I wanted to use the dual intercept method, I'm going to say, using the dual intercept method, for the y-intercept, we're going to let x equal 0, right? That means we're looking for f of 0, which is going to be 3 times 0 plus 2. 3 times 0 is going to be 0. You're going to get 2. Get into the habit of putting it in point form, which means I want you to write the y-intercept is 0 is to 2. That's good practice. Okay, cool. Now for x-intercept, right, I'm going to let y equal to 0, which is as good as saying let f of x equal to 0. So there's nothing wrong with either using let y equal to 0 or let f of x equal to 0, because y and f of x are essentially the same thing, right? Okay, cool. So now I'm going to proceed here back to my equation. Where it says f of x, I'm putting 0. I've got 3x plus 2, and I'm now going to solve for x. If I subtract 3x on both sides, I'm going to get negative 3x is 2. If you divide by negative 3, you're going to get x is negative 2 over 3. Like I said, get used to putting it in point form. Therefore, the x-intercept of this graph is going to be negative 2 over 3 is to 0. Very powerful. Right. Now I've got enough information. I can then start drawing my graph of f of x. Let's see what will happen if I do that. I'm going to call my Cartesian plane. Here's my Cartesian plane nicely. It's going to be rough, guys. Please bear with me. It is going to pass when y is positive 2. So let's add there. I'll just say this is 1 and that is 2. Let's have 1 and 2 here. Minus 1, minus 2, minus 1, minus 2, right? Okay, 1, 2, 1, 2, minus 1, minus 2, minus 1, minus 2, not 3. That's essentially what I need here. Okay, fine. So now it passes when y is 2. That's where it's passing. That's f of x. And it's going to pass at negative 2 over 3, which is 0 point something. So it's somewhere here. So my line is, let's just call a straight line. A nicer one will do. So this is my graph of f of x. A very nice graph, right? So let's, okay, I'll upgrade that. I'll have to upgrade that line, right? Okay, right. Let's move it so that it's passing nicely where it has to. And there we have it, Mawela. This is actually the graph of f of x. Powerful stuff, right? And then remember to label it, because if we are marking your work, we want to see who is who in your equation, right? That's the graph of f of x. Now I'm going to use this information to find the conditions for, or the properties of the inverse graph. I don't need to recalculate y-intercept and x-intercept for the inverse graph, because I know what happens between a graph and its inverse is that whatever is x becomes y, and whatever is y is going to become x. So what I'm going to do is, since we know the y-intercept of f of x is 0 and 2, it means for the inverse, right? For inverse, right? This y-intercept will become the x-intercept, which means my x-intercept is going to be 2 and 0. Notice I swapped them. Whatever was y, I called it x, and whatever was x, I called it y. What was y is now x. My y is now x. My y coordinate is now x coordinate. My x coordinate is now y coordinate. That's what inverses are all about. You just swap all the x's, you call them y's. You swap all the y's, you call them x's. Similarly, for the inverse, if you look here, we have the x-intercept of the original. That means for the inverse, instead of saying y-intercept, I'm now going to say the y-intercept, not x-intercept, right? And I'm going to swap them again. I'll have 0 here, and I'll have minus 2 over 3 as the y coordinate, right? So I have all the properties I need of the inverse graph. I don't need to recalculate them, because I'm going to have to just swap. Whatever was x becomes y, and what was y becomes x, right? So let's try and draw this information, or plot this information on our Cartesian plane. Okay, this graph is going to cut y at 2, I mean x at 2, there's 2 there on the x-axis. And then it's going to cut y at -2/3, there it's going to be at -2/3, right? It's going to be somewhere there, right? Okay, cool. So I've got all the information I need now. I can then try to draw this graph. Let me use my freehand drawing and try to be as accurate as I can be. So it's going to go something like that. And that will be the graph of the inverse of f of x. Very powerful. Now, once I'm done with this, we always want you guys, we want you to show the line of symmetry. That line, the mirror line, the line y equals to x, we want you to show that line. So I'm going to try and put it in blue here. So this line is a very special line. Right, we want this line, the line y equals to x. You can draw it dotted, you can draw it the way I did here. It doesn't matter. As long as we see the line y equals to x, most people draw it dotted. It is okay if you do that. We like to see that also as part of your drawing. So this is how you'll actually take the information of the original graph and convert it to the inverse. If they ask you to plot both the original graph versus the inverse, it is like even when they ask you to find the domain and the range of both the original and the inverse, you don't have to do it for both. Just focus on one graph. Find the domain of the original and the range of the original. What is the domain in the original will be the inverse, will be the range in the inverse. What is the range in the original will be the domain in the inverse. And that's how you would actually work with the next question. So we're coming back with more of these inverse graphs. I hope this has opened your mind in terms of how do you work with inverse graphs on a linear graph. There's more that are based on quadratics. There's also a very nice question that involves a lot of graphs drawn on the same set at the same time. You want to see how do you analyze that.